In this video, I'll explain to you how you can design the capacitor inside the buck converter. So in order to do that, we need to look at this part of the buck converter. So I will just go ahead and go to a part which is more zoomed in. So we have it here. So you can see that the current comes from the buck right here. And then it either has to go through the capacitor or the resistor, the load. So let's say that we assume that the voltage over the resistor is constant, because in reality, it's close to constant. Then we know that the current is constant because the current is basically the voltage divided by the resistor. And the resistor is also constant, so this means that the current is also constant. So that means that the average of the current coming from the buck converter goes to the load, while all of the ripple goes to the capacitor. So this means that this one is actually equal to the average of the inductor voltage, inductor current, while this one is equal to the ripple of the inductor current. And this is quite important to understand, because this determines the whole behavior of the output voltage, because we know that the output voltage here is equal to the voltage over the capacitor. So if we just look at the relationship between the current and the voltage in the capacitor, we're able to find how much ripple the current creates. So now I want to look at the waveforms. So I just first want to write up an equation for this. So we have the equation for the current, which is the capacitance multiplied with the derivative of the voltage over the change of time, or the derivative of the voltage with respect to time. And I actually want to simplify this a bit, because so that we can interpret it a bit better. So let's say that the change of voltage is actually the ripple of the voltage. So delta VO. So this is the ripple, it's the peak to peak voltage here. And then we can have a look at the change of time. Let's say that is from one peak, from the bottom to the top. So let's say this time here. So here you can say that it's 10 microseconds, this period. So this is the dt. And one period, this is actually 1/2 of a period, because one period is from here to there. So one period is from there to there, right? That is one period of the waveform. So then we know that the change of time, dt, is equal to the period over 2. And now this is actually equal to 1/2 times the switching frequency. So we're more interested in the switching frequency because that is a design parameter. Now this starts to become a little bit messy, but I think we're done on this side of the equation. So the derivative is basically, I'll just write it up here, the ripple of the volt multiplied with 2 times the switching frequency. And the current is equal to this. So that is what we have right now. So now we want to look at the current. So remember earlier that I said that the current is equal to the ripple of the frequency. Now you can see here that this is actually the ripple of the frequency, where you just take the average to 0, right? You just make the offset so it becomes 0 on average. And if you do that, you can see that here we have, this is the ripple of the current, which is delta IL, and then the amplitude here becomes equal to delta IL divided by 2. And now remember that we are only interested in this period here, right? 1/2 period. And during that period, what is the average capacitor current? Well, because it's basically a triangle, it would be half of the amplitude. So therefore, we know that the capacitor current, now this become a bit messy, where we can continue down here. The capacitor current is equal to the ripple of the current divided by 4, because the amplitude is is half of the ripple, while the average current is half of that again. So then it becomes the ripple divided by 4. And now, if we just continue with this part here, we can see that this becomes equal to the change of, or the ripple of the voltage multiplied by 2 times the switching frequency. And we forgot the capacitance. So we should multiply with the capacitance here and multiply with the capacitance here. We forgot it to move it from here. So if we now solve for the voltage ripple, we will actually get this equation that we have down here. This is what we get if we solve for the voltage ripple. So in order to design the capacitor, we actually design the ripple that we want using this equation. So we could either solve for the capacitance if we want, or just adjust the capacitance until we get the ripple that we want. And now the switching frequency is often determined for something else and not for this voltage ripple, but that would depend on the system that you're designing, like what the buck converter is used for. So that is basically how you can do this. And if you're interested in this buck course, you can go into the link in the description. And in my next video, I will go into some losses. What losses do we have in the buck converter, which is the chapter 4 that you can see here. And if you're also interested in trying out this, to open up the simulator and try it out, where you can see the ripple in real time, where you can just run it, you can go into the description below. So here you can see that if we increase the capacitance, it's kind of hard to see, but you reduce the ripple.